A calculation of forces in multi-span statically definable beams and determining the diagrams of the forces and moments is lesson number 210 from the article 210 of the book Mechanical Systems Calculations of the Marine Facilities. First of all, we have to consider the static definition and geometric changeability or unchangeability of the beams in the mechanical systems. The dependence of static definability of number of hinges is illustrated by the examples of hinged cantilever beams on the draft 2.10.1. The dependence of static definability on the number of hinges is illustrated by examples of the hinged cantilever beam. For two support statically definable simple beam, statically definable draft 2.10.1a. So we have the beam supported by the sliding hinge on the right and the fixed hinge on the left. The single statically indefinable two-span beam, draft 2.10.1 on the right, B, supported the same as by the fixed hinge on the left and the sliding hinge on the right, and one more sliding hinge in the middle. So this is static indefinability of this, because the number of the degree of freedom is less than 0. The sample of triple statically indefinable four-span beam is four-span. The support is a fixed hinge, the right one supports sliding hinge, and three more sliding hinges within the span of this beam on 2.10.1c. And multi-span statically indefinable beam is multi-span beam because more hinges we have. 1, 2, 3 hinges connecting the parts of the beam. The number of hinges of statically definable hinged cantilever beam can be found by the formula of Chebyshev in particular, showing the number of degrees of freedom. The number of degrees of freedom equal to product 3 by number of disks. Disk is a geometrically not changeable part of the mechanical system minus product 2 by number of the simple hinges of connecting the disks in the mechanical system, minus C0. C0 is the number of the simple support hinges. So, for example, the sliding hinge is the support hinge, simple support hinge, simple support with one projection of the reaction on behalf of the support, and the fixed hinge we can correspond with two support with the two hinges sliding one, because the fixed hinge provides the two components of the support reaction in the point A. If we assume that the number of disks of the multi-span beam is number of the hinges plus 1, number of the hinges connecting the disks in each couple between, then using the Chebyshev formula, we can find that the number of hinges is a number of the simple support hinges minus 3. The examples of geometrically invariable hinged cantilever beams we have on the draft 2.10.2a and b. With the supports, we do the hinged cantilever beam geometrically invariable due to the supports, because with no support it will be variable as well. geometrically variable. In order for statically determined the hinged cantilever beam to be geometrically unchangeable or unvariable, the following conditions must be met. Each span of the hinged cantilever beam cannot have more than 2 hinges. So we have here 2 hinges within the span. Between these two supports, there are 2 hinges, no more than 2 hinges have to be. There cannot be 2 hinges in each span in the adjacent span. So we have 2 span here and 1 span in the adjacent one span, and 1 hinge in the adjacent one span. But there cannot be 2 hinges. The number 3, the adjacent span cannot be without hinges. There cannot be more than 1 hinge in all the span with another hinged support. There must be at least 1 hinge at the end in the outermost span with a rigid embedment. So we have rigid embedment and at least have to be 1 hinge in the span. The primary and the secondary elements of cantilever beams. To calculate the support reactions, bending moments, and shearing transverse forces in the cantilever multi-span beam, we usually can have the so-called floor diagram. Floor diagram consists of the basic and the secondary elements. The basic elements of cantilever beam are those which remain geometrically unchanged when adjacent elements are removed. The secondary elements of cantilever beams, due to the insufficient number of support connections, are not remain geometrically unchanged when the adjacent elements are removed. So let's consider the example of the use of the floor diagram to find the diagrams of the bending moments and the shearing forces of multi-span cantilever beam. So we have assigned multi-span cantilever beam. We can see as well the distributed load and assigned of 2 kilonewton by meter. From the point A to B, we have concentrated force 6 kilonewton. And we have another one distributed load as 4 kilonewton per meter at the last cantilever span of 2 meters. So use the floor diagram. Starting from the left, we have to decide is considered one span the basic or the secondary one. It is basic if if we remove the next one and all adjacent span. The next one is from this point of T1 to B. If we remove this one second span and the left one remains unchangeable. Yes, because we have the rigid embedment here, the left one span remains unchanged. So, and if the next one span is secondary, we draw it above the basic one of the left, starting from the left. If it would be basic again, so we have to put it below. So starting from the left, we have that the basic one span A. On the if we remove the adjacent element, the next one from the point from the point of T2, the joint of the hinge T2, we will remove this one. The next one span will not be will not be unchangeable. They can change because we not support it changes. Geometrically can the support reactions are not enough to make this from the hinge T1 to T2 unchangeable part of the cantilever multi-span beam. So we draw it above the previous one, What about the next one? Exactly, it is a secondary element because if with not the supports, it not can be geometrically unchangeable. So we substitute the hinges of the connection of these parts of the cantilever multi-span beam by the fixed hinged supports. The left one here, the right one here for the interval between the hinges T1 and T2. And as well, we do the next one here about the right one with not the left one, the previous. The right one remains geometrically unchangeable due to the right one part of the mechanical system. So the next one is basic in relation to the previous one from hinges 2 and 3. So from the hinges 2 and T4 is a basic element. So we draw it below the previous one, secondary element of the hinged cantilever beam. And what about the right one? Yeah, and we connected as well each of parts of the hinged cantilever beam by the fixed hinges here. Fixed is not a simple hinge sliding, but fixed hinges with two connections. What about the next one part from the point T4 to the point G? Is basic as well, because if we remove the previous one, this part remains unchangeable, geometrically unchangeable. So we put it on the draft below the level of the previous one span of the multi-level hinges cantilever beam. We put it below. After that, we can do decide and define the forces in the hinges. Starting the upper one, we consider these hinges as just a supports, and we find the reactions of the supports considering the load over the external load over this span from the hinges T2 to T3. After that, we can make a bending moment diagram as we have here. That the reaction is 3 kilonewton, the right one 3 kilonewton, vertical reaction, and because we have no the external load of the horizontal components is just a multi hinged the cantilever beam, so we have only transverse load external. So the reactions we have here on the left 3 and 3, and on the stretched fibers of this part of the total beam. This part is upper one, and on the stretched we can make a diagram of the bending moment. The bending moment here in the middle is 3 kilonewton by the arm of 3 meters here. So we have the maximal magnitude of the bending moment here 9, and after that it reduces to 0 because here we have the hinge. And besides, we can do the shearing forces. If we start from the left, the shearing force is 3 kilonewton to plus. After that, it remains 3 because we have no distributed load here from the hinge T to the point of application of the force F. And after that, we have 6 the step down, 6 kilonewton, the force action of number 6. And after that, we have as well the evenly distributed diagram of the shearing forces. Considering this reaction of got for this one upper one, the part of the cantilever multi-hinged beam as the force acting on the left and right span from this upper one. So the force acting 3 kilo, we can do the diagrams of the bending moments for the left one and the right one first we have to decide about the support reactions in this hinge and this hinge and this hinge and this hinge. We can consider the equations of balance, maybe a rotation of this part, this beam around the point T1, and the rotation due to the force of reaction R2, but acted on this one part of the multi-hinge cantilever beam to the down direction. So is of the another sign than the force acting on the upper one of the floor diagram, upper one span of the total system, mechanical system of the multi-span cantilever beam. Finding these reactions, considering the equations of balance here, we can do the diagram of the shearing forces and the bending moments. Bending moment here is 0 here because this is hinges, and the shape of this part of the diagram is parabolic of the quadrat parabola, and the curvilinear, and this one is linear because it's for bending moment, because here we have the area of the evenly distributed shearing force starting from 3 kilonewton due to the reaction of the support of the assumed support here between these two spans, this the basic span to this one. This one is not basic. This one, the secondary element of the cantilever beam. After that, we can find this diagram of the bending moment, because minimal correspond to 0 magnitude of the shearing forces, because these two diagrams are into the derivative relation. This one is the integral function of this of the shearing forces. The bending moments are integral function, and the shearing forces derivative of the bending moments. And for this part of the distribution of the even distribution of the transverse, the external load, we have the parabolic, and this linear of the shearing forces, and parabolic for the forces, for the bending moments, excuse me. After that, we can assume that the left one reaction is 2.5 kilonewton, due to the decision of the equation for the left one, considering the force T2 got previously from the upper one level. Next, we consider here, and for example, we can find that the reaction in the point T2 have to be 2.5, considering balance of all efforts acting previously got as considered as the external load from the upper one level. T2 acting on the right one point of the the span T1, T2, and we got the reaction here of this assumed hinge, fixed hinge, as 2.5 kilonewton. We have here, this is the force, external force acting on the left one span of this multi-span cantilever beam. So for this one left, we have distributed load Q1, and we have the force acting downwards. Here the reaction is upward, so this force is downward acting on the rest part of the left one cantilever beam with a rigid abandonment. For this kind of the distributed load, we have the diagram of bending moment like that, and besides, we have this is together with the action of the force. So this force gives us the linear diagram, and the distributed load gives us parabolic diagram with the convex due toward the action of the distributed load. So, and the force increases the negative shearing force in the left one span, because the shearing force caused by the reaction R1. comes from the previous one span, R1 as a reaction got of assumed fixed hinge for the floor diagram. And we next have the left one part of the shearing forces. In magnitude, it increases due to the action of the distributed load, but in the same direction as the force from the previous one span acting to the left one. Okay, going to the right, we have forces here on the right part of the upper one floor, of the upper one level of the floor diagram. The force in the hinge T3 is equal to 3 kilonewton and acts on the span between T3 and T4, and we can do the balance equations for this part of the multi-hinged cantilever beam, and we find that the force acting on the left part here, R3 is 3 kilonewton, yes, from behalf of the middle one span, but to another direction than the force in the floor diagram acting on this part of span acts upwards, and due to the external force acts downwards. Here, this acts downwards as one-two part of half of the acting external load in the previous one span. So we can keep considering this and doing the diagram, the shearing forces and the bending moment. The bending moment diagram is linear due to here we considering the balance equations for the span in the supports C and the T4 support, and we got the direction of R4. We can consider the total rotation moment around the point C have to be equal to 0, and considering the external loads or action in the joint T3 with the previous one hinge, with the previous one span, and we can find the direction T4 is equal to 1 kilonewton, and we can find the direction in the support C is only vertical reaction because the support C is a simple hinge, sliding hinge. The we make diagram of the bending moment. The force 3 kilonewton by the downward by the by the arm 1 meter gives us 3 kilonewton by meter product as magnitude of the maximum magnitude of the bending moment here on the support C, and after that it reduces to 0 because hinge at 0 gives us 0 bending moment, and the angle of inclination of this part of the diagram of the bending moment, the angle corresponds to, with the sign minus, it reduces the moment. This corresponds to only, we can, this magnitude 3 divided by the arm 3 and find that the angle is, the tangent of the angle is equal to 1 kilonewton. This is a shearing force diagram for the span from the hinges T3 to T4. Keep going to the right, and we can consider this right one shearing force in the hinge T4 as the force of 1 kilonewton acting upwards in the hinge T4 on the right one span. So we consider the balance equation for the right one span, and we can find directions in the supports D and E. The support D give us 11. How to do that we know because we consider, for example, for finding the reaction in support E. First of all, it can be in support E. We consider all efforts, the left one upward effort with a span 1 meter. with the arm 1 meter relative the point D, and the right one we have with the arm 3 point of the part 2 meter is only half because the concentrated force applied in the middle of this distribution segment EG. So 3 point plus 1/2 of 2 is 4. So the force is of 2 meters H distributed load of the 4 kilonewton by meter and per meter for the extent of 2 meter action give us H, the force H with the arm rotating this part from T4 to G, this part of the beam of the total mechanical system that rotates this part with around the point D with the arm 4 meter, 8 kilonewton to 4 meter rotating clockwise. So the R4 rotates the right one span clockwise, and we can find that reaction here is 11 kilonewton, the reaction of acting on this hinge on the support E. And we can go to creation of the, for example, the first we can do the shearing forces diagram. Upward 1 on behalf of R4, 1 kilonewton, no distributed load, so even distribution until the reaction 4 upward, the 4 downward is directed downward. 4 we have no distributed load upward, we have 3 and H, we have 11 kilonewton step, 2 step, 1 step and another step. And the shearing force at the end is 0 because we have no force, concentrated force applied to the end. So we have this kind of these 2 steps and 2 parts of evenly distribution and 1 part linearly reduced magnitude distribution of the shearing force. And this gives us the bending moment diagram for the first on the stretched fibers. 1 kilonewton by, how is that 1? 1 is a force, and the part of the application is the 1 meter only is this arm, the bending moment. After that, we have the change of sign of the bending moment, and we have H, and we have from 1 to H because for 3 meter. This is 3 meter is if you divide the magnitude of 3 is kilonewton, the magnitude of this part of the shearing force, and this corresponds to tangent of the inclination of this for 3 meter inclination is 3 Newton. So we have the change of the sign, and we have another one magnitude from 1 this minus 1 to plus H kilonewton by meter product. And the next we can find the area of this triangle in this area, and this comes to 0. We have no hinge here, we have no support at the end, so it comes to 0. This is a parabolic curvilinear part of the diagram of the bending moments. And now having the diagrams for each of spans of the cantilever multi-hinged cantilever statically definable beam, consider using the floor diagram, considering that if each span of the considered span is statically changeable, so cannot be is geometrically changeable, so it cannot be on the same geometry with not the support of the adjacent from the left. part of the beam, so adjacent span. So this is changeable. If changeable, we draw it to the upper. If not changeable, we draw it below here. So this is not changeable with one support, and the right one supports with not with the T2, T3. If we remove T2 to 3 from the beam, the span from T2 to T3, this part will not change geometrically. So starting from the upper one level, we next can determine the diagrams for each of the spans of the considered cantilever statically definable multi-hinged beam. After that, we can combine the total diagram of the bending moments and the shearing forces, considering all good diagrams and as a superposition of all good diagrams. So we have from the left one diagram, from the right one. So we can have for all assigned cantilever multi-hinged beam the diagram of the bending moment and the shearing forces. Questions and comments. Static definability of hinged cantilever beam depending on the number of the hinges. We can use the formula, maybe the formula of Chebyshev, to find the number of degrees of freedom, and is a necessary requirement for the for this equality to zero is necessary requirement for the mechanical system. We have to be statically definable. Statically definable. The good number of the freedom have to be zero. It is statically definable. Necessary requirement. Determination of number of degrees of freedom of mechanical system by Chebyshev formula. Yeah, by the Chebyshev formula, we have three summands. First is product of number of disks as unchangeable parts of the mechanical system plus two numbers of hinges connected these disks in the mechanical system plus a number of the simple hinges of the supports of mechanical system. Geometric variability of hinged cantilever beams. Geometric variability of cantilever beams is that we can assume what is the conditions of unchangeable, geometrically unchangeability of the beams. So if they satisfy the considered assumption that each span of hinged cantilever beam cannot be more than two hinges, that there cannot be two hinges in each span in the adjacent spans. The adjacent spans cannot be without hinges. There cannot be more than one hinge in other span with another hinges support. There must be at least one hinge at the end of the most span with a rigid embedment. So this is geometrically unchangeable span, unchangeable beam. And if the span do not satisfy these rules, these conditions, this span, the geometric, the hinged cantilever beam is geometrically variable. Conditions of the geometric invariability of a hinged cantilever's beam. Yes, we did consider that. Primary and secondary elements of the cantilever beams. Primary is geometrically not changed elements. So if you remove the adjacent elements, this do not change the geometry. So this remains unchangeable. That is why we cannot do any displacement of any points of the unchangeable element if with not only the deformation of the element. In the floor diagram, we have a primary and secondary elements. The primary is unchanged element, secondary is a changed. Changed which can be geometrically changeable without the mechanical deformations. If only we remove the adjacent element, the change it is a secondary. Application of the floor diagram to calculate a multi-span statically determined beam and to make diagrams of bending moments and the shear forces is a very applicable the floor diagram because starting from the left, we can consider about each part of the multi-hinged cantilever beam as is it part changeable or unchangeable. If it is not changeable, so this is a basic element of this multi-hinged cantilever beam. So the next we decide about the next one. If it is not changeable, so for the for statically definable, exactly we are talking about only the statically definable multi-hinge cantilever beam. If the next one is not changeable, so we have to indicate it on the floor diagram below. If it's changeable, we have to put it up on the floor diagram. Then the previous one unchangeable. And we do this all in the sequence, and we can find the upper one element. Starting from that, we can we can decide about the forces and acting on the upper one element in the floor diagram from behalf of the adjacent from the left and right part point elements of the total cantilever beam. And these forces we use in the external load to determine the bending moment and shearing forces diagram for the upper one element. And this is a first. And the second, we use the forces as the external load for the left and right one basic element, which is not changeable relative to the considered upper one element of the statically definable multi-hinged cantilever beam. So forth we can find the diagrams of the bending moment as combining of the diagrams for each span of the statically definable multi-hinged cantilever beam using the floor diagram to find the communication of the efforts from the upper one changeable element to other elements of the total mechanical system. Thank you.